Well, hello, welcome again to our journey into algebra and number theory, and this is the second video in this section on congruences and congruence classes. So we looked in the previous video at the idea of congruence, and we defined this set Zm, which was the set of numbers from 1 up to 0 up to m minus 1, which were the possible remainders when you divide an integer by m. Well, we can perform addition and multiplication as usual, remembering that we're wearing our mod M glasses, so we always have to take the least residue of our answer. So, for example, if I've got my mod 7 glasses on in Z7, 5 4s are 20, but modulo 7, that's the same as 6. So you can multiply two integers in Z7 and you end up with an integer back in Z7. You can add two numbers, 6 plus 5 is 4, modulo 7. I always say to my students, don't show this to your younger brothers and sisters in primary school. They'll be very confused to hear that 6 plus 5 is 4, if they don't know about mod arithmetic. Well, we can construct addition and multiplication tables for this, much the same as one did back in primary school. So I've done here an example of Z4 and Z6. Z4, I've done an addition table. So if we simply pick two elements, so 2 plus 2, for example, is 0 mod 4, and 3 plus 2 is 1 mod 4. So this is the addition table. Now, just enjoy the table. It has some interesting properties here. Every number occurs exactly once in every row and column. So this is a Latin square that we have here. Interesting, we get on the main diagonal here, we get all threes. Interesting observation, we get 0, 2, 0, 2 on the other diagonal. The multiplication table for Z6 is slightly more interesting. You'll notice it's not a Latin square. We certainly do get every number between 0 and 5 along this row and down this column. And by the way, of course, both of these are symmetric because A plus B and B plus A, and A times B and B times A are the same, modulo M. The bottom line's interesting. We get the numbers backwards. As we got the top line 1, 2, 3, 4, 5, we get 1, 2, 3, 4, 5 backwards along here. There's not a Latin square because we're getting in this row, for example, we only get 3 and 0. And we'll see later on, we might like to compare and contrast that with the multiplication table of, say, Z7, which I'll look at in a moment. So it's easy to see that Zm forms a ring under addition and multiplication. That is, you can add or multiply two elements of Zm and you stay inside the set. And there's an identity element, 0 for addition, there's a 1 for multiplication. So these form these are examples of finite rings. We're going to write Zm star for Zm take away 0. See, 0 is a little bit of a pest here. When you multiply anything by 0, you get 0, so it's not really that interesting. So I'm going to put Zm star for Zm take away the 0. But that will of course, you'll need to have a 0 to be a ring, so this will no longer be a ring, but we'll have a look at what its structure is in a moment. Consider the multiplication table now for Z7 star, that is Z7 take away 0. Now this is really more interesting because we get the numbers straight across there in order, and we get them backwards along here. We get them straight in order here, backwards here, by symmetry. But notice that it is a Latin square. That is, every number appears exactly once in every row and column. So in particular, if I wanted to know 2 times what gives me 1, then I can read off 2 4s are 1. And in fact, every number has a number that multiplies with it to give you 1. 3 5s are 1, 4 2s are 1, 5 3s are 1, and 6 6s are 1. So every element x in Z7 star, there's exactly one element corresponding to it, an element y, that multiplies together to give you 1, well, modulo 7. Perhaps I should write that there, just for to be pedantic, modulo 7. In other words, 5 3s are 1, 4 2s are 1, etc. Now that's very interesting because that didn't happen for Z6 star. If we remove these two, we do not get a Latin square, and so if you look along here, there's no number you can multiply 3 by to give you 1. There is for 5, and there is for 1, but not for any of these other numbers here. So this is rather special. We call this y the multiplicative inverse of x. So if I give you an element x, is there an element y that multiplies by x to give you 1? If so, we call it the multiplicative inverse of x, and we're going to write y is x inverse. In Z6, only some elements have inverses, 1 and 5. In Z7, every non-zero element had a multiplicative inverse. So we're going to extend our idea of a ring now to what we call a field. So a commutative ring F with a 1, in which every non-zero element has a multiplicative inverse, is called a field. So in particular, Z7 is a field, but Z6 is not a field. You may have possibly come across this word, well, perhaps not in first year, but before. You probably met this word field perhaps before in your mathematics, where it was used to refer to the set R of real numbers or C the set of complex numbers. These are examples of infinite fields. The fields we're going to look at currently are in fact finite fields. The set Q of rational numbers is also a field, and we'll look at a little bit more of at infinite fields a bit later on in one of the later sections. We're going to concentrate here for the moment on finite fields. So here's our second theorem. Lovely result. You've got Z sub P is a field if and only if P is a prime number. So enjoy that theorem, that's a lovely theorem. ZP is a field if and only if P is prime. And it's worth giving a little proof of this one. So it's if and only if, so suppose we've got P as prime, then we want to show that this is a field. We know it's a commutative ring with a 1, we just have to check every element's got a multiplicative inverse. So if P is prime, A is an element of ZP star, that is a non-zero element of ZP, then the GCD of A and P is 1. So by Bezout's lemma, we can say there are integers x and y, so that I can write the GCD of these numbers as an integer linear combination. That is, there's an x and y such that AX plus PY equals 1. That means then that if I now put my mod P glasses on, then that term with the P in it disappears and I have AX as 1. And that tells me that A has an inverse, namely X. And this X is in ZP. Once I read it modulo P, it'll belong to ZP. So that says if P is prime, every non-zero element in ZP has an inverse. Conversely, if ZP is a field and P is not prime, we'll try and get a contradiction here, then P, we can factorise P and into A times B, where they are integers and neither of them is 1. Now also this A has to be somewhere between 1 and P, and B has to be 1 and P. So A and B are in ZP. Now, since ZP is a field by assumption, then A inverse exists. So that means if my P is AB, I can get my hands on B by multiplying both sides of this by A inverse. So B is A inverse AB. But now AB is P. And this is congruent to then modulo P, this is congruent to 0. So B is 0 mod P, and that means that P has to be either 0 or P, and that forces A to be 1, but B can't be 0, so B has to be P, that forces A to be 1, and that's a contradiction because neither A nor B was 1. Little example, want to find 101 inverse in the ring Z257. So an exercise for you to do. The GCD of these two is 1. So you'll apply Euclid's algorithm to this to get U1. Write down your Residue identity and then put on your mod 257 glasses to work out what the inverse of this is. A little definition here, an element A in a ring. So we've seen that in general in the ZMs some elements have inverses, some don't. If P is a prime, then all elements have an inverse, but if you're in a general ring, an element A which has a multiplicative inverse is called a unit. So we're going to, out of my ZM, where some elements have inverses and some don't, I'm going to pull out the ones that have inverses, and I'm going to call that U sub M, U for unit. So UM is going to denote the set of units in ZM. And we're going to be looking at the structure of this. This UM, in fact, turns out to be quite interesting, and we'll have a look at its structure later. So in a field, every non-zero element is a unit. In other words, so for example, if I had U sub P, then that will be Z sub M star. Every non-zero element here is a unit. Sorry, that should be a P there. U sub P star. Every non-zero element in ZP is a unit. So in Z6, the only units are the ones with inverses, and we saw that was 1 and 5. So we're going to write U6 is 1 and 5. U8, the only elements with inverses are 1, 3, 5 and 7. 2, 4 and 6 do not have inverses modulo 8. And as you might guess from looking at these examples, the numbers that don't have inverses, 2, 3 and 4, well, these have a non-unitary GCD with 6. And the ones which don't have inverses here are 2, 4 and 6, and they don't have unitary GCD with 8. And so you might guess the following rather, again, lovely theorem here that pins down exactly what this U sub M is. So the elements of UM that have inverses in ZM star are precisely those that have a GCD of 1 with M. So looking back to the example here, the numbers that have a GCD of 1 with 6 are 1 and 5. The ones that have a GCD of 1 with 8 are 1, 3, 5, 7. So again, a little proof of this. So firstly, I'm going to suppose that the GCD of X and M is 1. Then once again, we can use Bezour's lemma to write the GCD as an integer linear combination of X and M for some integers A and B. Put on your mod M glasses, that disappears. I have AX is 1, and that means X has a multiplicative that says X has multiplicative inverse A, which belongs to, if I read it modulo M, belongs to, sorry, that was correct the first time. So X has a multiplicative inverse, and that means X does belong to U sub M. Conversely, if X is in U sub M and the GCD of X and M is D, then we're assuming that X has an inverse, so X inverse is in Z sub M. That means X times X inverse is 1 mod M, i.e. that says X inverse minus some multiple of M minus Km is 1 for some integer K. Now we've got D divides X and D divides M, so D divides 1. Well, not too many numbers that divide 1. D has to equal 1. So we can see that U sub M contains precisely those elements of Zm that are relatively prime to M. As I mentioned before, U sub P is ZP star for whenever P is prime. So a simple example, if we've got U15, we simply write down the numbers that are relatively prime to 15. So that's 1, 2, 3 is not, 4 is, 5 is not, 6 is not, 7, 8. We exclude 9 and 10. We have 11, 12's got a GCD of 3, 13, 14. So that's 1, 2, 3, 4, 5, 6, 7, 8 elements in this set. And we're going to study this later on. An interesting question, obviously, that arises: can I tell how many elements there are in this set without actually listing them all? We'll have a look at that question fairly soon. So in the next recording, we're going to have we're going to study the structures, or to study these sets U sub m and Z sub m in some detail in this and the next section. And we'll stop that here, and we'll introduce in the next video the notion of a group.